I suppose we were talking about induction the other day, no? At last. So, I told you that there are several inductions, no? Forward induction, strong induction. What else I cannot remember. Backward induction. We have to prove them today and finish it induction and began analysis type thing. By next Friday we have to finish everything about sequences, not the series. So see, we are not going to go to series now. I did one or two problems from induction, no? Yes?
Yes, I think so.
Can I see your book? You write them? No.
No, sir. The note you gave.
Yeah. You need this one. Okay, thank you. So, let's prove the principle of mathematical induction because as long as you are in this class, you can say it is an axiom. But when you go out of this class, you may be asked to prove it. So as a result, you need to know how to prove it. And there is a thing we use, well ordering principle, well ordering. Principle. Every non-empty subset of Z plus has a least element. This is clear, no? If you take this is a subject, it has a least element. Z plus is again a subset, it has a least element, that is 1. If you go for even integers, like this, it has a least element means smallest element. No? So it is a good axiom. We don't need a proof. In a sense, so sometimes I say nothing can be taken for granted in mathematics, but this L-ordering principle is taken for granted. There are other equivalent statements to this. Actually, this one and principle of mathematical induction are equivalent. They mean the same thing. Anyway, let's prove the small induction. Because to you, writing style, you need to improve. So you need to look at what I write when I am writing a group. So let's say I might forget if I write it in my own without looking at the book. What is it? This is preliminaries. This and that. Principle of mathematical induction. Induction. Let P and be n. In my case, I write sequence this way. He writes n going some m to infinity. No? I mean, this is so much of writing. So I will show it by writing. Let Pn be a sequence You know sequence, sequence of statements. Where for each n belongs to n. For each n belongs to, we say plus. Pn is a meaningful statement about n. About n. Meaningful means it doesn't have Lalita is a nice girl. This sort of statements are there. Pn is a meaningful statement about. Assume that P1 is true. This is the principle that you use in A level also. No difference. Only thing is that in A level it's not written correct. For each n belongs to n. If Pn is true, then Pn plus 1 is true. So we are three things are assumed. Pn makes sense for any n. P1 is true. At the same time, if by any chance for any n, if Pn is true, then Pn plus 1 is true. Conclusion is then for each n belongs to n, Pn is true. Intuitively, this is correct. No? And P1 is true. First one, P1 is true. From here, it says if P1 is true, then P2 is true. Therefore, P2 is true. If P2 is true, then P3 is true. Therefore, P3 is true. Like that, you can go. But, and so on, eventually you have to say. You cannot write a proof that way. So, and so on, so forth. They are not mathematical statements, but it what is going on? Again. It is ruining my time. I don't want to waste time in chat. So, yeah? So we need a proof. Can you? Now, anyway, I can write this. It doesn't work well, at least we can close it. So, somebody might say, why do you need a proof that it can be taken for granted? But in maths, nothing can be taken for granted. The statements we take for granted are called axioms. However, according to yellow book, not only yellow, and red book, it is an axiom. But for us, the thing is this: when you go to university, it is not an axiom. Either you are, if they don't teach you how to do it, you have to do it in your own, or else you have to look at the book. One way. So I will write, actually proof is not difficult, we are going to use this line to prove it. Let's say let f is equal to, set of all n belongs to Z plus, such that Pn is false. I use the letter capital F, false, because of false. If I had written n belongs to Sheshat such that Pn is true, I would have used the letter T. So what I have to do is that I have to prove that F is empty. So suppose, for sake of contradiction, that F is non-empty. Now you can see F is non-empty, F is a subset of Z plus. Then this one says every non-empty subset of Z plus has a least element. By well-ordered in principle, there is a lot of things you do today by well-ordered in principle, because I need to spend more time with epsilon type things, but these are essential. By well-ordered in principle, F has a least element. Least element means smallest element. Right? So by this, clear. So least element say M. So M belongs to F. Thus, M cannot be 1, no? P1 is true, no? Therefore, F has a least element. Thus, M belongs to F. Since P1 is true, M is not equal to 1. M cannot be 1. Therefore, M is strictly greater than 1. Right? This is the reason. Thus, M minus 1 greater than or equal to 1. No? If M greater than 1, M must be at least 2, no? Minus 1 greater than 1. However, we know that M minus 1 belongs to Z plus. Not good to say in that. Hence, I always thinking of buying away. But when I go home, I forget. These things are not good. Hence, M minus 1 belongs to Z plus. M is the smallest element, so that Pm is true. Therefore, for M minus 1, Pm minus 1 is, no, Pm minus 1, M is the smallest integer, such that Pm is false. Therefore, Pm minus 1 must be true. Thus, Pm minus 1 is true. Right? However, M minus 1 is an integer. Pm minus 1 is true. This says, if it is true for some integer, it is true for the next integer. By 2, of the principle of mathematical induction. Cannot write. PM is true. That's belongs to when I should have written here. No need to write, but anyway. PM is false. M is the least element. No? PM is false. Here I have get PM is true. Contradiction. So I suppose, for sake of contradiction, that F is non-empty. Thus my supposition is false. My supposition is false. Hence F is empty. That means thus Pn is true for each n belongs to n. So after proving the theorem, you can use the principle of mathematical induction to solve any problem. For some problems you cannot use it because the statement is incorrect, simply because it's not going to help us. So I am not going to solve any problem here because I want to save time. I will give you a problem. Then I would like you to write the solution on a piece of paper. Next Wednesday, I want to see. But you need to be very careful because can you see, I write everything. I don't delete anything. I haven't taken anything for granted except the fact that well-ordering principle. I haven't proved well-ordering principle because it is a, I am not the man of mathematics, no. Well-ordering principle is a principle. So this is the problem that I want you to do. But you have, when you are using the induction, you have to write your Pn precisely. Let Pn be the statement. Then you have to show what? P1 is true. Then you have to prove this line. Both of them need to be proved. Then you can conclude that Pn is true. So I want you to write very careful solution to see whether you do it or not. This is a very simple problem. You can do it even now, but don't do it now. Let Xn be the sequence of real numbers such that I have written, no, it's not such that satisfies what each n belongs to n. Xn plus 2 minus 5 xn plus 1 plus 6 xn equals 0. x1 is equal to 5 and x2 is equal to 30. Proof. by induction. By induction. That for each n belongs to n, xn is equal to 2 to the n plus 3 to the n. Very simple problem. I wrote through by induction because if you have done some differential equations, no. So if there are two kind of differential equations, difference equations. If you know difference equations, this is a very simple thing. So even if you know difference equations, I say prove by induction without using difference equations. I have to be correct, no? So you go home, so minus 5x and plus 1. X1 is 5, x2 equals 13. X1 is x1, 2 plus 3 is 5, that is correct. X2, 2 square plus 3 square is 13. That's simple. Okay. So I would like to see here solution that is very important. Next. So it has no epsilon, but it has some very important thing. So this is well ordered in principle. I told you for some problems you cannot use well ordered in principle. There is another thing called strong principle of mathematical induction. Sometimes you may have heard, sometimes you haven't. So let's do that also because that is very. In the university, I don't know whether it is too clear. I don't know. But who cares? I'm sure that here, you know, it very good. Principle of. Let's see how have I stated in the book. More on the principle of mathematical induction. We have covered this calculus and induction. Cannot remember the principle of true mathematical induction, true principle of. That's how we have written. Principle of true. Next one, mathematical induction. Again we say, can you see this, the power is this thing? Principle of mathematical induction, you should realize that it is a very powerful statement. Because we have to prove infinitely many statements. P1, P2, P3, P1000, P million and 1 and so on. So if you were to prove one by one, I mean till you reach Nibbana or till you reach heaven, you won't be able to do it. So this is so powerful, immensely powerful principle. So people don't realize, actually the thing is with the A-level teachers, they don't say precisely. The reason is that they haven't learned it well in the universities. Now, you two are learning from me, so you two must be the best in this thing. Let Pn be a sequence of statements where for each n belongs to Z plus Pn is a meaningful statement about n. Assume that P1 is true for each n belongs to n. If P1, P2, bingo, Pn are true, then Pn plus 1 is true. You cannot use, I just said by induction, not the strong one, only the simple one, using that only. If you want, you can do this way. Yeah, it's good to do. First, show it by induction. Then solve it by principle of strong induction. Then I will see whether you understand statements in maths. If P1, P2, Pn are true, then Pn plus 1 is true. Then for each n belongs to Pn is true. That's the theorem. Two different, no? First one said P1 is true. That statement is common for both the inductions. And first one said for each n belongs to n, P1 is true, then Pn plus 1 is true. Here for each n belongs to n, P1, P2, Pn are. P1, P2, Pn are all true at all. Are all, how is my English? Not good, no? How do I have it? It doesn't matter. If P1, P2, Pn are all are true, are all true. Are all, let's look at that way. Then Pn plus 1 is true. Actually, then because these two are inductions, you may wonder whether they are telling the same thing. In the other words, are they equivalent? They are equivalent. I am not going to prove it, but I am going to prove this one because we are going to use it. You have to use it quite often. I am Grace, it doesn't matter. Strong induction and normal induction, they are equivalent. I mean, if you find 310, because you have to do so many homework, so you may not have time. But if you can prove that they are the same, that's very good. Because I am trying to make you think mathematically and write mathematically. Okay. Proof. Again, let capital F, same thing. Set of all n belongs to Z plus. Such that at least one of LEAST one of, you copy down the problem. One more. At least one of P1, P2 up to Pn is false. I mean, if you want to say n belongs, 3 belongs to this set, then you have to say P1, P2, P3, out of these 3 statements, 1 is false. At least one. If you want to say 4 belongs to this set, you have to say at least P1, P2, P3, P4, out of these 4 statements, at least 1 is false. Right? So the set is clear. Now, as before, we want to prove that actually F is empty. You want to show that all of them are true, no? We want to prove that. We want to prove that capital S is empty. To the contrary, assume that assume that F is non-empty. F is non-empty. Thus, capital F is a non-empty subset of leaving. That's capital F is an unempty outside of P set plus. Again come to the well ordering principle. By well ordering principle. Ordering principle. PRI principle. F has a least element. F has the least element. M. F has a least element M. Thus, what do we know? M belongs to F. Least element is a member of the set. It's not like soup, not like that. Thus M belongs to F. Since M belongs to F, then at least one of, thus at least one of P1, P2, bingo, PM is false. Right? M is in this set because if you consider the M statements, P1 statement, P2 statement and so on, PM statement, at least one of them is false. However, since P1 is true, like before, because when you take, when n is 1, at least one of P1 is false means P1 is false. When n is equal to 1, you have only 1 here. Since P1 is true, m is not equal to 1. Thus, m greater than 1. Thus, m greater than 1. Hence, m minus 1 belongs to Z plus. Since m greater than 1, m minus 1 belongs to Z plus, and m minus 1 does not belong into it. Because m is the least element, m minus is not there. If m minus 1 does not belong into F, then what can I say? If an integer n belongs to F, then P1, P2 all the way to Pn, at least one of them is false.
Then you can say all the P1 to Pn is true.
Thus, good anyway, but still slow. P1, P2 up to Pn minus 1 are all true. No? These are all true. However, then according to the pi 2, then next one is true. Pi 2 Pm is true. Which is a contradiction? Oh, there, I said Pm is, what did I say?
P1 to Pm is false.
P1 up to Pm,
At least one is false.
one is false. Now I have Pm is True. Is there a contradiction?
Yeah, now P1 to PM all are true.
Therefore, P1 to Pm all are true. Second contradiction. Anyway, this completes the proof, and I want to make it short. Originally we said that P1 up to at least one of P1 up to Pm is false. Now we are saying P1, P2, Pm are all true, so that is a contradiction. So I have proved that it's from mathematical induction. There are some problems you cannot do by normal induction. You have to use the, I may give one or two. Even the problem that I wrote on the board, that problem can be done by the normal induction. First I want to use the normal induction, then use the strong induction. Either way. Some problems you cannot do it by the normal induction. Some problems you cannot do. Right? So, I will have to wait for the next day to do.
Sir,
Yes.
sir, in the first part we say that Pn is true. So in the second part we also say if P1 to up to Pn are all true,
Yeah.
can we remove the Pn in the second part?
Pn or P1.
Sorry, P1.
If you want, yeah. Because P1 is true, and you can do that. You understand this question? But this is how we write. Although you are correct, of course there are problems. I will not do any problem today. So I want you to think about this thing, but to the contrary, if I do one problem, that's good for you. These are long calculations, so that's why I want to spend time. Of course, there are other little versions of this. But before leaving, can I do one question? I have to go through it. Anyway, I have wrote it. Now you may wonder, what? You may wonder. Now, actually, you proved that well-ordering principle implies strong mathematical induction as well as the normal mathematical induction. Now, you may wonder, strong mathematical induction, does it imply the well-ordering principle? Are they the same? All of these are the same. I mean, they this southern Sri Lanka, they have these devil dances. In the morning time, they are just called 18 Sinhala word is the heart of Pali. Same man comes in 18 different ways, but the same person. So it is kind of funny. I don't know whether they are still. So it is another result that well-ordering principle and principle of mathematical induction are the same. So I would like you to try to show, if you have time by the way, because you are busy with the homework, I know that. But these 2 weeks you are not doing the problems from the book, no.
I have no more this week.
No, I did not give you. Not from the book. Not from the book. I have it some. So these are not from the book. I just wrote them because I guess I thought you kind of got tired of time from the book. So this is good that we are spending 2 weeks to make us kind of mathematical rather than Star Wars. Axiomatic introduction to real numbers. Now, anyway, I want you to prove well-ordered principle of normal mathematical induction and strong mathematical induction are the same. They are equivalent. And I want to prove that and this well-ordered principle are the same. We have to prove that also. Then we have to spend we have to spend a bit of time with the backward mathematical induction. That is also we need. By the way, though there are many statements, normal induction, forward induction, backward, strong induction, and there are other varieties I am not writing here. Backward induction, they all are equivalent, but appear in different ways because some problems you cannot do. These are four because you are going Pn to Pn plus 1, or P1, P2, Pn, all of them to Pn plus 1. So these are forward. Backward induction is going backwards. However, they are equal. So that's the funny thing. So now let us prove that. We have seen that well-ordering principle implies this, the strong mathematical induction. Now, let us show that the strong mathematical and that the principle of, we have shown. Now let us show that the principle of strong mathematical induction implies the well-ordered principle. So these are not only analysis, we are doing group theory. Everywhere these are used, induction and well-ordered principle. Used everywhere. So now we are going to do that. Okay? Here I hope the strong mathematical induction was proved using the well-ordered principle. No, that's why I said we have seen that well-ordered principle implies the strong mathematical induction. Now let us show that the principle of mathematical induction implies the well-ordered principle. Okay, now let me erase this thing. So, assume, proof. Assume the principle of strong mathematical induction. Now we have to prove that well-ordering principle. Can you guess how to prove? And do you have an idea? Assume the principle of strong mathematical induction. What do I have to prove?
For each non-empty subset of Z plus, there is an least element.
Yeah, very good. Every non-empty subset of Z plus has a least element. That's what I have to prove. So let's assume that's not true. Assume. Rule the pins are kind of. Is this one? Yes, no? Assume. Now assume. It is not the case that every non-empty subset of Z plus has a least then what is true?
That element is strictly greater than 1.
No, I said now assume it is not the case that every non-empty subset of Z plus has a least element. I am assuming what I have to prove is wrong. So then I am asking, then what is true?
Then every non-empty subset of Z plus has a least element.
I am going to hit you.
It's a negation.
I am saying now assume, assume it is not the case that every non-empty subset of Z plus has a least element.
Some non-empty subset of Z plus has a least element.
No. Buffalo, New York.
So it says it is not the case that. So
It is not the case, that means that line is wrong. When I say, somebody says, he is a nice person. It is not the case that he is a nice person means he is not a nice person. That's what it means. Because this is how we write in English.
there exists non-empty subset of Z plus such that it doesn't have a least element.
Very good, but due to more time than expected. Hence, there is a non-empty subset capital A of Z plus which has no least element. Right? There is an unempty subset capital A of Z plus which has no least element. It does not have a least element. Capital A is an unempty subset of Z plus. Right? Capital A is non-empty. Capital A is a subset of Z plus. And however, capital A does not have a least element, means the smallest element. Now, we are going to use the principle of strong mathematical induction. As a result, we have to have some PE, no, if we want to use it. So, what is your guess about our PE? Let Pn be the statement. What is it? First we have to use the strong mathematical induction. There is only one statement that we can think of writing. What is it? You must be thinking about it. So, the reason I am doing all of them is to make sure you think logically and write logically. And on the other hand, of course, these are not proved in general, so we have to know the proofs. However, what we are doing is very advanced. But you two are advanced people, no?
Still, strong induction is not enough blood yet.
No, for the time being, of course you have seen only the normal induction. The statement, when you are thinking of the statement, it has nothing to do whether it is strong induction or normal induction. But what you said is very important we need to talk about one or two. Spend a couple of minutes about it. He said it is not in his, didn't get to his blood, but normal induction says P1 in any induction, not any induction, normal induction and strong induction. First assumption is P1 is true. That won't break. In normal induction, if the statement Pn is true, then the statement Pn plus 1 is true. In the second one, we say P1 up to Pn all are true. Then only I guess my English is incorrect, but that's how we talk, no? Then Pn plus 1 is true. If by any chance P2 is not true, we cannot use it. P1, P2, all the way up to Pn, all of them are true. Then Pn plus 1 is true. That's different from that one. Again, I ask you to show that they are equivalent. If you cannot do it, it's okay, I will do it. Not today, because now I am doing necessary things in order to proceed in our course. P and B the statement, but
For each n belongs to a n is strictly greater than 1.
Pn is a statement about n. What is your n? Pn?
Pn is the statement for each n belongs to a.
It cannot be a universal statement. I have given you the word universal, no? Pn is always a simple statement, not universal. It's an open statement. Did I give you the word open? It's an open statement. It's not universal, it's not existential. No, it is just a simple open statement.
N is greater than 1.
And if you say n is greater than 1, it has nothing to do with the capital N. Can you guess?
A non-empty subset of Z plus with n elements has a least element.
Non-empty.
A non-empty subset of Z plus with n elements has a least element.
Unempty subset of Z plus with n elements always has a least element. I mean, we are not with this book, by the way. We are doing normal maths now. Let me get me the statement. N doesn't belong into it. Look. Let's see this pen again. This pen again. N doesn't belong into it. So usually you have course. I'm not putting course because it takes time. Now I have to show that P1 is true. Can you show that P1 is true? This is my Pn. N doesn't belong into it.
Yes, P1 is 1, so 1 does not belong to A because it doesn't have least element.
Okay. 1 doesn't belong into A. Why? If 1 were belong to A, then A has a least element. 1 cannot be a member of A and cannot be a member of A. Member element. What is the other one? Cannot be an element. One cannot be an element of A because if one belongs to A, then A has a least element. Thus, 1 doesn't belong to A. Hence, P1 is true. Right? If we wrote some Pn, I don't know whether it will work so far. Somehow, we wrote some Pn and we have proved that P1 is true. Now let n belongs to Z plus. Suppose that what?
We are doing the strong induction.
Yes.
Suppose that P2 is 2.
Suppose that what? I have taken n belongs to Z plus.
Pn is 2.
Oh! I guess I am asking too many questions from you.
P1 to Pn is true. All are true.
P1, P2, bingo, bingo, Pn are all true. P1 up to Pn are all true, right? In this strong induction. Thus, 1 doesn't belong to A, 2 doesn't belong into A. Bingo, bingo, bingo. N doesn't belong into A. Right? Now what do we have? I have to prove.
Pn plus is
Pn plus 1 is true. What is that? Pn plus 1 is true means what?
N plus 1 doesn't belong to it.
I want to prove n plus 1 does not belong to A. Suppose n plus 1 belongs to A by any chance. Then what will happen? Then we know that 1 is not in the set A, 2 is not in the set A, and so on, n is not the set A. And another thing we know about A, it does not have least element. Now, having taken for granted this n facts, if I assume n plus 1 I want to show that n plus 1 doesn't belong into A. If I assume n plus 1 belongs to A, what will happen?
It gives a contradiction.
Eh?
It gives a contradiction.
It is a contradiction. Why?
I mean, it will be the least element then.
N plus 1 will be the least element. If n plus 1 belongs to A, then n plus 1 will be the least element of A. Thus, then n plus 1 will be the, which is a contradiction. Which is a contradiction. Hence, n plus 1 does not belong into A. Thus, Pn plus 1 is Pn plus 1 is true. So now what do I have shown? I have assumed P1 up to, I have proved P1 is true. I have assumed P1 up to Pn are all true. If true, then Pn plus 1 is true. Thus, if P1, P2, bingo, Pn are all true, where is my key? Then Pn plus 1 is true. We have shown P1 is true. Let's say this one is some alpha. This one is beta. From alpha and beta, and beta, for each n belongs to n.
Is it?
Yeah. For each n belongs to Sn plus Pn is true. For each n belongs to Sn plus Pn is true. That is, for each n belongs to n, n doesn't belong into it. For each n belongs to n, n does not belong into A. However, I said, when there is an unnamed subset capital A of Z plus which has no least element. So no n of Z plus belongs to A. Therefore capital A must be
Empty.
empty. hence capital A is empty. I will write, this completes the proof. So I have, now do I have to write more? This instead of writing this completes the proof. That's it's not good. It is good but not good also. Anyway, so thus every non-empty subset of C plus has a distributor. So I assume the principle of strong mathematical induction. Thus every non-empty subset of Z plus isolation I have root. Assuming strong mathematical induction I have root well ordered principle. So assuming well ordered principle I prove the strong mathematical induction. Assuming strong mathematical induction I prove the well ordered principle. So they are, even though they appear different, they mean the same thing in mathematics. Right? They mean the same thing in mathematics. So I would like you to do, or I may do it, not today. Today I am doing necessary stuff to continue our lessons. Someday I will come back and do that, or I can assign it as a problem also. Anyway, these are very good mathematics. You understand, no? Something you have to make sure that sometimes you cannot write the negation, that's not good. But now you must be a big shot. Anyway, let's see. I always say that by 2-3 months you will be like that, but not today. Now what? I have to do principle of backward induction rules, otherwise it is incomplete. After backward induction, you can go to sequences. Let's complete anyway then. Over. Now, yeah, only backward induction. This takes time, but anyway, I must do it. Can I wish? Yes?
You always ask that question after starting to.
Yeah, after erasing someone. Another thing, I have a habit. Do you want a book? No. That's my way of doing. I ask you, do you want? Would you like to have some pizza? No. Because I ask the question, I myself reply. And my husband, my wife says, you ask the question and you immediately reply. I have nothing to do. It's good. I want to finish the principle of mathematical. Backward induction. That in Tao's books you heard about axiom of choice. No? Axiom of choice is equivalent to many things. These books are very, very good. And we don't need it now anyway. So, backwards induction. Backwards. My spelling is wrong. backwards C1, BACK, WACK. It's not backwards. Backwards induction. Let Pn be a sequence of meaningful statements. Meaningful. I have to go to English class. Meaningful statements. Let Pn be a sequence of meaningful statements. Assume that. Let me check the book there. I am forgetting something. Two. Backwards induction, backward. Issue backwards 82. Let me be sequence of the algorithm. Let P and be a sequence of meaningful statements about n, let's say. Assume that Roman 1 P of 2 to the n. Let's write this first. For each n belongs to n. P2 to the n is true. 2. For each n belongs to n, if Pn plus 1 is true, then Pn is true. Then for each n belongs to n, Pn is true. So backwards because of this. So far Pn is true. If Pn is true, Pn plus 1 is true. Here Pn, if P1 plus 1 is true, then Pn is true. However, we are using, not using, we are proving P2 to the n. P2, P4, P8, P16, all of them are true. We have to prove that. Then this one is true. Now you can, now once I prove 1, P2, P4, P8, P16, P32, all of them are true. Once I prove the second one, I haven't proved any statement is true, but I will have proved if Pn plus 1 is true, then Pn is true. So, since after proving first one, I have proved P4 is true. Therefore, P3 is true. I have proved P8 is true. Therefore, P7 is true, P6 is true, P5 is true. Like that, all of them are true. So, here argument is different from forward inductions. Can you see?
So does it always have to be the n to the power of n? So 2 to the power of n?
I'm sorry, I didn't get it.
Should it always be the 2 to the power of n in the first step?
No. He's asking very intelligent questions. It can be any strictly increasing sequence. So, this is enough for us.
It is always greater than n plus 1.
A second one is if Pn plus 1 is true, then Pn is true, that remains the same. But the first one, as you asked, I mean, this is a very special case, 2 to the n. It is, let me see. I mean, you can do it actually, you can prove it. Yeah, I must have written, I got tired of proving. I have written it down somewhere. Anyway, your question is a very good question. It is any strictly increasing sequence. Yeah, right. Oh, I have written here, let NK be a strictly increasing sequence of positivities. Then P and K is true. Okay. Like in other words, if you want 2 to the n can be replaced by 3 to the n. By 2 to the n has other advantages for us, particular advantages, but you can replace 2 to the n, 3 to the n, 4 to the n is strictly increasing sequence. Alright, then proving this thing has more work here. Anyway, we have to prove it. Then the important thing, now you can see now how it works. First we prove P2, P4, P8, P16 is true. Then second one we prove if Pn plus 1 is true, then Pn is true. If somebody asks you how do you know that P15 is true, you say from the first one P16 is true, from the second one then P15 is true. It is like that. So we have to prove it. So what time is tea time?
10:50.
Now it is 10:50. When should I start? Now or?
Now it's better because I put the order already.
Okay.